Good morning, everybody. Where are we here? What have we been doing? Well, we spent half of the week, roughly, to derive the 3+1 decomposition. That led us to a system of equations that is equivalent to Einstein's equations. And it splits into two groups. We've seen there was one group that are the constraint equations. There's the other group that are the evolution equations. Yesterday, what we did is we talked about techniques that we can use to solve the constraint equations. Guess what? Today, we'll talk about techniques that we can use to solve the evolution equation. And here they are. Okay? So this is our last chapter. And that chapter is solving the evolution equations. Now, if we stare at these evolution equations long enough, we realize before we can do anything here, we have to make certain choices. Does anybody know what I'm talking about? What choice do we need to make? We need to choose a lapse and we need to choose a shift, right? Again, that encodes our coordinate freedom, so we need to choose a lapse and a shift. Einstein did not give us that lapse and shift, so we have to come up with some choices. Now, usually you start with something as easy as possible, right? So why not, okay, actually maybe I should write this down first. Okay, we need to choose the lapse and the shift. The fancy way of saying that is we need to choose a slicing. That amounts to choosing a lapse. Okay? And we need to choose a spatial gauge that also drives home this connection with gauge theory. Okay, so a slicing and a gauge. That means we need to choose a shift. Okay, so again, why don't we choose something as simple as possible? What is the simplest choice that comes to your mind? Lapse equals 1, right? And beta equals 0. Exactly. Okay, so why not? Not alpha equals 1 and beta I equals 0. Okay. What do we know about our time congruence, about our time vector then? TA, how was TA defined? Exactly, it was alpha NA plus beta A. Now you told me I should choose alpha equals 1, beta equals 0. So now we actually see that our TA is exactly the same as NA, right? And remember, we spent many hours discussing whether these two things are the same thing, right? In general, they are not, but it's exactly for this coordinate choice that they are the same thing. Okay? So exactly for this choice, the coordinate observers TA will be coincident with the normal observers NA. Right? So let me write that down. The coordinate observers are the same for this choice as normal observers. Okay? What is the acceleration of the normal observer in this case? Actually, right, how do we define the acceleration? Well, we define that as AA equals NB grad B NA. Remember that? But didn't I ask you to derive a neat identity so we can express this as something else? What was that? Okay, it was dA, the spatial covariant derivative of the log of the lapse, right? So now we see immediately that the acceleration must be 0. Okay? Now what do we call observers who have 0 acceleration? So they're freely falling. So what kind of trajectories do they follow? Geodesics, right? So that means that these normal observers now follow geodesics. Okay. So I'm sorry. Yes, the normal observers, but by virtue of this statement, also the coordinate observers. Okay. So the coordinate observers now follow geodesics. i.e. they're freely falling, right? They're just freely falling. They follow geodesics. And that explains why we call this particular slicing geodesic slicing. Because in this particular slicing, coordinate observers are freely falling. Okay? In a different context, the same slicing has, or the same coordinate choice has other names. For sometimes in the context of cosmology, for example, it's called Gaussian normal coordinates. Okay, but fine, right? Why is this bad, actually? This is bad because any non-zero gravitational field, what does it tend to do to freely falling objects? It tends to focus them, right? So imagine here's a star, then, well, things are freely falling, they will all fall towards the star, okay? So that means that these coordinate observers, they will get closer and closer. That will ultimately lead to a coordinate singularity, okay? Now let's do another example. Imagine maybe we have even a weak gravitational wave, okay? So let's say we start out with some gravitational wave packet. Then, maybe it's centered in this region at t equals 0. That gravitational wave packet has gravitation fields. It carries energy. Energy is the same as mass in relativity. So this actually exerts a gravitational force on everything else. That means even just having a gravitational wave, observers, freely falling observers, will start to fall towards that point, okay? Now the wave may disperse, okay? It may disappear and we end up with flat space, but our observers, they have started moving towards each other. So if it's now flat space, they will continue to coast, okay? They're not accelerating anymore, okay? But they will continue to coast and they will still form a coordinate singularity. So that means that even for very weak gravitational fields, after a finite amount of time, this choice of coordinates automatically leads to a coordinate singularity, okay? That's basically exactly what you do not want in a coordinate choice, okay? So therefore, even though this is the simplest choice possible, it's also, probably one of the worst choices possible, okay? This will not work, okay? So actually, let me write this down. So this leads to the focusing of coordinate world lines, and hence to coordinate singularities. Okay? And that means that your code will crash very soon. Okay? So the code will crash very soon. In fact, on the tutorial this afternoon, I'll let you work out a time limit, okay, after which you're guaranteed to have encountered a singularity, okay, for a weak gravitational wave. Okay, that you can do that analytically. In fact, you will find that you get an integral, which you already saw on Monday in the numerics lecture, as an example of a singularity that gives example of an equation that gives you a singularity after a finite amount of time. Okay, that's exactly what you get here. But anyway, that's geodesic slicing, and that's why you should stay, at least in general, you should stay away from geodesic slicing. Let's try some alternative. Okay, so as an alternative, we could try something that is called harmonic slicing. Okay. And by harmonic slicing, we usually mean that the time derivative of the lapse equals minus alpha squared k, and we also choose beta equals 0. Okay? In fact, this is a special case of harmonic slicing, which of harmonic coordinates, which I'll get back to later. Okay, I'll tell you where this comes from exactly. Okay, this choice, actually, in this choice you can get an analytic expression for the lapse. You can see what it is as a function of time. You can integrate this equation analytically. I'll also ask you to do that this afternoon in the tutorial. Okay, that's a simple little calculation. Okay? With this choice, things will be better in general. Okay, so now you can evolve things, for longer. Okay? This is better. But in general, if we chose a code that implements these equations as I wrote them down here, the code will still crash. Okay? I'm not saying that's guaranteed. There may be specific cases where that's not the case. But in general, this set of equations, if you coded this up, okay, it will still crash. Okay? So, but in general, codes that implement the ADM equations is still crash. Okay? And of course, if you just observe your code crash and you don't know at all why that is, maybe there's a bug, maybe you've mislabeled your indices, probably you've had some experience doing that this past week in your tutorials, right? There's many ways of introducing errors into the code, and maybe you think maybe that's just a bug and you just need to find all bugs. Or maybe you're not treating the boundaries correctly. So there are many different ways of trying to figure out what is wrong. And actually that held up the field of numerical relativity for many years, okay? Coming over what is wrong with those equations. Now it turns out that we can reformulate those equations. We can rewrite those equations and bring them into a different form, and then all of a sudden things work a lot better. Okay? So we can do the following. So what we have found is this. Okay? But okay, we have found so-called reformulations that work. Okay? I.e., I mean, that work is a very loosely defined expression, right? But what I mean is now you can evolve weak fields and neutron stars, whatever. Okay? What do I mean by a reformulation? Well, how can I bring these equations into a different form? Well, really, there are two different ways how I could do that. I could, for one thing, I could introduce new variables that, for example, absorb already first-order derivatives. So remember, for example, where are actually the second derivatives? What is the most important term in these equations? It's here. It's the Ricci tensor, because this Ricci tensor, that's where the second derivatives are. So we could introduce new variables that absorb already some first-order derivatives, and we could express, some second derivatives in terms of first derivatives of those first-order variables. We could do that. Okay. The other thing that we can do is we can add the constraints, because we say, well, the constraints have to be analytically, they have to be satisfied. They have to be satisfied at any time. So we can always add some rehashing of the constraint equations to these evolution equations, and that may also affect how these equations behave. Okay? Now, I will spend a good time of today's lecture explaining why it is that that could possibly help. Actually, let me first write this down. Okay? We could introduce new variables. Okay? Or we could add constraints to the evolution equations. Okay? Now, anybody in their right mind should ask, how can this possibly help? Okay? What do I mean by this? Because after all, I'm just using identities, right? I mean, clearly the physical content of these equations must be exactly the same. Yes, I can rehash these equations, I can come up with some reformulation, but of course, whatever system of equations I come up with must be identical to these equations in a mathematical sense, equivalent to these equations. Otherwise, we're not dealing with Einstein's equations anymore, but we do want to solve Einstein's equations. So you should ask, how can this be? How can this have any effect? Because if I have a solution to my original set of equations, then surely I can get a solution to my reformulated equation, and they should be the same, right? So how can this make a difference numerically? Okay? And there are two different ways of thinking about it. If we ask our mathematician friends, they will tell us, oh yes, well, that is because these equations have certain mathematical properties. These mathematical properties are a result of basically the highest order derivatives. Okay, but now if we add constraints, actually we could count the order of derivatives, and it turns out that we're adding, again, second order derivatives. So basically what happens is that we are affecting the highest order derivatives. That means we're affecting the principal operator, and that determines the mathematical properties. And while one system may be well defined, the other one may not be well defined, or well posed, and that means in one case we may be guaranteed that there exist the well-defined solutions, and in the other case we may not. Okay? And so fine. Okay, but that may not be all that intuitive to us, okay? So what I'll do today is I'll give you what I find a much more intuitive kind of argument that shows you why it is that if we use different formulations, we get different numerical behavior, okay? At the core of this is the following observation. It is true what I just said a minute ago, that if we have a solution to one set of equations, that analytical solution will be an analytical solution to the other system of equations too. Okay? Otherwise, we have made a mistake in the reformulation, right? But that's not really the relevant question if we're doing numerical work. Because when we do numerical work, we're always dealing with the analytical solution plus a little bit of numerical error. Okay? So it is true that the analytical solution will behave the same, that will be the same, but the numerical error may not be the same. We have no guarantee that the error in one system will behave in exactly the same way as the error in the other system. So what we'll do is we'll look at error, okay? We'll look at so-called constraint violations. We will ask what happens if we have a little bit of a constraint violation. What happens to that? And we'll see if we use a reformulation, they behave differently. Okay? Now this sounds like kind of a scary proposition because these equations are pretty complicated. Here's the beautiful thing. We'll do all of this for Maxwell's equations because we see exactly the same effect in Maxwell's equations. So we'll spend a good time today just talking about Maxwell's equations, which we've probably all seen before, and we'll see exactly that effect analytically in Maxwell's equations. Okay, so what we'll do is let's actually step back and let's talk about evolution equations in general. Okay, so evolution equations. Okay, so let's talk about the simplest evolution equation that comes to my mind, and that is a scalar wave. And that should be an old friend of yours by now, because I believe you've done a lot with the scalar wave this week on the numerics class, right? So what is the scalar wave? Well, we can write it as a block operator acting on psi. That is in flat space-time, right? This is just flat space-time, so this is second time derivative plus the Laplace operator acting on psi equals 0. And for numerical work, it's, again, a good idea to bring this into to rewrite this second order in time equation as a set of first order in time equations. So I will define a new variable kappa, and for reasons that will be clearer later, I'll actually define it as the negative of the time derivative, okay? And then I get a system of equations, you know what, that I'll write over here, okay? Then we get this partial t psi equals minus kappa, and partial t kappa equals minus Laplace operator acting on psi. And let me ask you, is this the form of the equation, how you integrated the wave equation in the numerics class? Okay, so right, so this is what it is. Okay? Maybe up to the minus sign, okay? But now we could implement this numerically. You've actually done that. As long as you use a numerical method that is suitable, okay? You've noticed that you can integrate this, okay? And you get beautiful numerical solutions. You can watch this wave propagate, and it's all quite lovely, right? So basically, in principle, there are no problems in the numerical integration. And if we we're all excited about this, and we told our mathematicians friends about this. They would tell us, well, what do you expect? I mean, it's a symmetric hyperbolic equation. Symmetric hyperbolic equations are well posed. That means that they're well-behaved solutions, so there should be no problem at all. Okay, this is an example of a symmetric hyperbolic system which is well posed. That means that the solutions are well behaved and all is good. Yes? Sorry? I cannot hear you. I'm sorry. Say it again. What is the problem? Okay. Okay. So I still don't know. I apologize. Okay, but is it okay? Okay, good. All right. Okay, now where am I? Okay, so that's the scalar wave. Okay, and nothing particularly exciting happens there. So let's look at the next type of evolution equation that comes to our mind that might be interesting to look at. That is electromagnetism. Okay, so let's talk about E&M, Maxwell's equations. Okay, so usually we write Maxwell's equations in the following form. Electromagnetism. Okay, and what I mean is in flat space. We could, of course, also look at electromagnetic fields in curved space-times. That's not what I have in mind here. We just consider it in Minkowski space. Okay. Then we can write down Maxwell's equations. We have the two constraint equations, y equals 0. Probably you're more used to writing this as the nabla dot E in vector notation, okay? But it builds character to do this in the index notation, so we'll just do index notation because we're already used to it, okay? So the evolution equations are partial TEI equals the curl of B. If we write the curl of B in index notation, we get what symbol? Levisivita, right? So this is the antisymmetric tensor there, djbk, and then we get a minus 4 pi ji, and we get a partial t bi equals minus epsilon ijk djek, right? If I got the signs right. Okay. Now, for the comparison, both with the scalar wave and the ADM equations, it's actually useful to express this equation in terms of the vector potential. Okay? And I'm sure you've done that before too. So we'll write B as the curl of a vector potential A. Okay? So we have a vector potential BI equals epsilon ijk djak. What happens to this constraint if B equals 0 then? That's automatically satisfied, right? And you can see that if we took a covariant derivative with respect to di here, we have a di dj that is symmetric in flat space, but ij is antisymmetric, so that is 0, right? So we have di bi equals 0 automatically. Now we have to deal with these two terms. Let's actually look at them. Okay. And what is the curl of ijk djbk equals? Well, that's now the curl of A. And actually, let's just do some index gymnastics, right? See how this works out. So this is ijk epsilon k lm dj dl am. Now, what do you get if you take the curl of the curl? Something. What do you get? What? It's the gradient of the divergence minus the Laplace operator. Let's see how that comes out of this. Okay. So, how do we deal with this thing? Do you know what that is? Exactly, exactly. So that's exactly how this pops out, right? So this is a delta I, L, delta Jm, minus delta Im, delta Jl, right? So if we insert that, then we see that we get two of these terms now. And these two terms have the indices kind of flipped, right? So one of them is dj, di, actually maybe I'll, yeah, it doesn't matter. dj, di, a, j, yes, okay, minus dj, dj, ai. And now, if you look at this, this is dj, dj, so this is a Laplace operator acting on a. This is more clear if we flip the two. If we have a dj, aj, that's a divergence, and then we take the gradient with respect to I. Okay, so that's what you're used to. Okay, but now we've seen how we can derive the same thing in index notation. Okay, all right. Then also we have this. We have epsilon ij k dj partial t a k equals minus epsilon ijk dj ek. That is the last equation. That's this one, right? If I take the time derivative of b, that is now the time derivative of the curl of a, which is the curl of the time derivative of a, which is this term, right? And now we see that, aha, we could almost, just cancel these epsilons, okay? And then we have an equation relating these two, but we realize we have to be careful because of the epsilon. We can always add another vector to this, which has zero curl. And a vector that has zero curl, we can write as the gradient of a function, right? So this implies, therefore, that partial t ak equals minus ek minus some gradient of some new gauge function phi. So this is how the gauge freedom entered into this problem, right? So this is our free gauge function. Okay? So our evolution equations then take the following form. Okay, we have evolution equations are partial t ai equals minus ei minus di phi, and we have a partial t ei equals minus dj dj ai plus di dj aj minus 4 pi ji, right? And I remind you basically that perhaps you're more used to seeing this term as a Laplace operator acting on A, and this term as the gradient of the divergence of A. Okay? Actually, let's stare at this for a little bit. This is actually kind of neat. Okay? So, let me see. Okay. Let's first compare. See, now we have three sets of evolution equations on the blackboard, right? So, here are the ADM equations. Here are Maxwell's equations. And here's our scalar wave. Okay? Actually, let's compare these two first. You notice that, aha, this is kind of the same thing. Basically, I have partial time derivative of AI equals minus, notice something, that's why I chose the silly minus, okay? So that we have directly this minus correspondence. Equals minus the second variable. Then we take the time derivative of the second variable, and it gives me a Laplace operator of the first variable, this one, right? That's exactly what we have here. The time derivative of the first variable is the second variable. Time derivative of the second variable is the Laplace operator of the first variable. Okay, so we could basically we could write a little dictionary, if you want, that tells us how to identify things. And we see that if we translate between Maxwell's equations and this, we would identify AI with psi, and we identify EI with kappa, right? Okay. Now what you notice also is that, aha, but there's another thing that is different here, okay? There are a couple of things that are different. One is this gauge freedom that I now have, okay? There's also a matter source, but that's fine because I could have also added the matter source to my scalar wave equation. That I'm not worried about, okay? But the real key thing is this new term. Okay? Now let's think about that. Basically, before I told you that these equations are completely unproblematic in numerical integrations because they're well posed, they're symmetric hyperbolic. This form of the equation combines to a wave equation for our variable psi. Okay? That is no longer the case here because now we have this additional term here. It is these additional second derivatives which basically spoil the wave character of this set of equations. If it were without this term, then you would see, oh, this is exactly the same thing. Look, for every component is time derivative of the first variable is the second variable, time derivative of the second variable is the Laplace operator of the first variable. But now I have this extra term. Okay, so it's this term that actually spoils the characterization of this equation as a simple wave equation. Okay? So this spoils the characterization as a simple wave equation. Okay? Let's also compare with GR. Okay? What do we see in GR? Well, look, it's again the same structure. Here's the first equation, the time derivative of our first variable, which apparently now we have to identify with AI. So here's the dictionary for translating Maxwell's equation into GR. We have to identify gamma ij with AI. And then this is equal to, and again, a negative, except now we have an extra factor 2 floating around, an alpha, okay? But here's the second variable. So basically we also identify kij with ei, right? Right? Now, look, here's the gauge variable, which now plays exactly the same role as the gauge variable here. It's even a derivative of a gauge variable, just like it's a derivative of the shift here. Okay? Right? So it's an exact correspondence. So if you want, we can even write that. Okay? How about this equation? Well, here's the time derivative of the second equation equals, now for Maxwell's equation, we see we have second derivatives of the first equation. Do we have those in here too? You can't really see them on first sight, but are they hidden somewhere? They're hidden in the Ricci tensor, right? The Ricci tensor, recall, the Ricci tensor contains second derivatives of the metric, which was we identify with A. So the second derivatives of those terms are hidden in here. And you notice that you have exactly the same structure. Okay? Now, of course, they're nonlinear terms, and of course, okay. But basically, we have a very strong similarity, and that means this suggests that by looking at these equations, we can learn something about what we should do with Einstein's equations. All right. Okay. Let's look at something here. What I will do is, I told you that we can understand the fact the different formulations of the evolution equations give a different numerical behavior by looking at error. So now we'll define one measure of the error that we might get in a numerical simulation that involves Maxwell's equations. Absolutely. Thank you for pointing that out. You're right. I could say, I choose phi in such a way so that this term is exactly 0. Okay? What is that gauge called, by the way? Is it Lorentz or Coulomb gauge? It's one of the Coulomb, right? It's Coulomb gauge, right? Okay. So we could choose the gauge to do this, okay? And it turns out by the exact same token, I could also choose a gauge in such a way that these other mixed derivatives, second derivatives, become 0. Really, you don't want to do that, though, because the gauge freedom is a beautiful thing to have. Really, we want to choose coordinates so that we can actually evolve black holes. Okay? So we would like to maintain our gauge freedom so we can later choose the gauge freedom in a way that is optimal for the purposes for which we're writing this code. Okay? So we would like to come up with a way of dealing with these terms that does not use up our gauge freedom. Okay? But thanks for asking. That's exactly right. Yeah.
Suppose you had chosen the Coulomb gauge.
Right.
But then what about the counting? I mean, here you choose one equation.
Right, that's right. But basically, you fix one, and that is it's basically the divergence of A, right? So which is just one variable, okay? And you can fix that by choosing the phi, okay? And likewise, basically, you know what? Let's get back to that. It will be easier to talk about that in a few minutes, okay? Yeah. So what I want to do is this. I want to define a constraint violation as the following. I'll use a curly C for this, okay? And I'll define this as the divergence of E minus 4 pi rho, right? That means if the constraint is satisfied, then C is exactly 0. But maybe we use this now to check whether we have numerical error in our code, okay? Let's work out what is the time derivative of C, okay? So i.e. basically what happens once we have, should we have a non-zero constraint violation. Okay? So let me compute the time derivative partial t of C. Okay? Well, that is di times partial t of ei minus 4 pi rho times 4 pi partial t rho. Right? Just commuted the partial derivative with the di, and that's what you get. Okay? Now I can use the evolution equation. I insert this equation for my time derivative of E. And actually, let's just do this. Okay? What do I get? I get a di, and the first term is negative, so there's a minus, di, and then I have a dj, ai. Right, because now I have the indices upstairs, right? So I had to raise the index I here, right? So the I is upstairs now. The second term will be plus di, and then from here I have a di, dj, aj, right? There we go. And then I also get a term from this. So I can write this as minus 4 pi times ji, no, I'm sorry, the divergence, di, ji, plus partial t rho. Did I do this right? It looks okay? What happens with these two terms? Recalling that we live in flat space now, so we can change, they all commute. And now it turns out that, look, this is the gradient of the Laplace operator. It's the divergence of the Laplace operator of A, okay? And we can arrange these things in exactly the same way here. And it turns out that these exactly cancel each other. Do you see that? Okay. How about these two terms? As long as charge is conserved, which we all hope, right? This term will also be 0. This is by virtue of the what equation, by the way? The continuity equation. Exactly, the continuity equation tells us that this should be 0 too. That means that the time derivative of C is 0, right? That's probably an exercise that you've done before in an E&M course. This was always presented to you as great news, because what this means is that the constraints are compatible with the evolution equations, right? It means that if the constraints are satisfied at any time t equals 0, now you evolve your fields, and this guarantees that at any later time the constraints will still be satisfied, so all is well, okay? But now imagine we do this numerically, okay? So maybe we all evolve some data. There shall be numerical error, okay? That numerical error may basically lead to a non-zero C. And what does this now tell you? Well, if C starts being non-zero at some point, okay, because of some numerical error, it will remain non-zero because its partial derivative is 0, okay? So that means that you could have constraint violations building up, but they have nowhere to go. They will just hang around. They will stick around, right? Okay, so let me write that down. I don't think we need this anymore. So a non-zero constraint violation C will persist. Okay? And it will not propagate away. All right? Let me show you how we can use a reform. Yes? You know, I already couldn't hear you. Say it again. What is?
This is a good thing or bad thing? If C is not C will persist, means it is a bad thing. It will always persist in anything.
That's right. So basically, is this good news or bad news? Okay. Clearly, any evolution equation should be compatible with the constraints. So of course, it would be a very bad thing if even analytically, your evolution equation would give you non-zero constraints. That does not make any sense. So clearly, you need something like this. Okay. But what I'll show you in a minute is that we can reformulate Maxwell's equations in such a way that these constraint violations don't have partial t equals 0 anymore. What does partial t equals 0 mean, by the way? In a space-time diagram, that means that if I march up in the t direction, right, when t points upstairs, then nothing will change in this direction. So everything will be constant in this direction, okay? We could, for example, say, oh, you know, it would be much nicer if we had a formulation so that these constraint violations satisfy wave equations, okay? That would still be compatible with the equations, because if you had c equals 0 at t equals, c equals 0 at t equals 0, if C satisfies a wave equation, it's still compatible with the wave equations in the domain of dependence. But now, if in the course of a numerical simulation we build up some constraint violation, this constraint violation would satisfy a wave equation, and it would propagate away. And if we have suitable outer boundary conditions, it will just disappear. Okay? And we end up with zero constraint violations. Okay? So, I mean, let's not make too strong statements about moral superiority here, about whether this is good or bad. Okay, it's certainly you need something like this so that the evolution equations are consistent. The constraints is consistent with the evolution equations. Okay, but the point of this exercise that we're going through is to show you we can actually we can reformulate Maxwell's equations. The effect of that is that the constraints will behave differently, and that basically comes back to the point that I wanted to make. That is that numerically, different formulations may behave differently, even though the analytic solutions to the formulations are equivalent, but the error that you have on top of these analytical solutions, they behave differently. They propagate differently. Okay? To show you that, actually, that is pretty fast to see that, so let me just do that. I'll erase this. Yeah, maybe that was a bad idea. Maybe I should have kept the evolution equations, but you have them in your notes, okay? So let's consider a reformulation of Maxwell's equations. And I'll do that by remember what I told you earlier today? I told you you can derive reformulations basically in two ways. We can introduce new variables that absorb first derivatives of other variables, and we can add the constraints. Let's do both. Okay, so I'll start with introducing a new variable. There's a new variable, let me call it gamma. Okay, and this gamma I define as the divergence of AI. So there's your first derivative of one of the independent variables that we've had before. Okay, the important thing is that I now raise this gamma to being an independent variable. Okay, so I introduce this as a new independent variable. That means I should not do the following. I should not compute this variable at each level of t, at each time step from the data that I have. Instead, I should consider this an independent variable, just like E and A, and I evolve gamma together with the other variables. That means I need an evolution equation for this gamma, but we can derive that from the evolution equations of the other variables. Okay? So we derive an evolution equation doing the following. Okay? I say, well, I want the evolution equation. That means I want to know what is the time derivative of this variable. Well, from its definition, this is di partial t ai, right? But we had the evolution equations for ai gives us something like ei plus the gauge variable phi. So this is the same as minus di ei minus di phi. Okay? So now I've introduced a variable as a new capturing some of the first derivatives, spatial derivatives. Here's the evolution equation, but I still want to add a constraint to this. Okay? And what I'll do, just to illustrate what happens, let's add not the constraint times, but the constraint times a constant and see what role this constant plays. Okay? So we add a squared times c, which, well, c was the constraint violation, so that is a squared times di ei minus 4 pi rho, okay? Where a is just some constant. And then my evolution equation becomes this. I have partial t gamma equals, well, minus di ei minus di phi plus a squared c. By the way, why am I allowed to add this term? You could say, I cannot just randomly add terms to my equations, right? But why am I allowed to add this term? Because it's supposed to be 0 anyway. Analytically, it is 0, right? I'm just adding 0 in a particularly fancy form, okay? All right? So now C was, you have it in your notes, is D, the divergence of E minus 4 pi rho. We already have a divergence of E here, so this gives me a squared minus 1 di ei minus di phi minus 4 pi a squared rho. Okay? Because that's the evolution equation for gamma. Of course, we still have the evolution equations for E and A. And in the equation for E, we now replace this one term in terms of gamma. Okay? So the other evolution equations that we still have is partial t ai equals minus ei minus di phi, and partial t ei equals minus the Laplace operator acting on A, which is the nice term. And the not so nice term, that term now becomes di gamma. Okay, this term has now absorbed this ugly term, and I still owe you a 4 pi rho ji. Okay, so what we've seen is by defining a new variable that is the divergence of one of our variables, we can absorb the ugly second derivatives and the first derivative of this new variable. Okay, so far so good. What I'll ask you to do today in the tutorial is to derive how the constraint violation C behave with this new formulation. And what you'll find is the following. It's very interesting. You might think, oh, what has changed? It's still partial TC equals 0, but that no longer holds. Okay? Instead, we now find the following equation for the constraint violations. So we can show that C now satisfies a wave equation. Partial t minus partial t squared plus a squared di c equals 0. And interestingly, this constant a that I added here, okay, chose here, that ends up being the wave speed of this wave equation. Okay? So if you choose a equals 0, if we choose not to add any constraints, then we now still, the propagation would be along in the t direction. But this suggests that, oh, a would be a particularly nice choice, clear also because this term goes away. Okay, this term will be gone. But then, basically, the constraint violations will propagate at the speed of light. Okay? Okay, so now what does this tell you? So what we notice is that if now in the course of a numerical simulation we build up some constraint violation, this constraint violation will now propagate away. It will go away, okay? Unlike in the original formulation. Okay? So constraint violations propagate with wave speed a. Okay? And what is the whole point of this exercise? It shows us that different formulations behave differently numerically. Not because they have different analytical solutions, but because the error will behave differently. Okay? So we see that the formulation, the choice of formulation, affects the numerical behavior. Okay? So let me put a box around this. This is the key point from this exercise. And I think this is actually a great place to stop for a few minutes to take a little break. And then we'll see how we can use the same ideas to reformulate Einstein's equations and do exactly the same thing. In fact, it's remarkable how similar the manipulations are. We just have to remember this identification chart. Okay? So let's take a couple minutes break. Right? So basically, what I was trying to motivate with this example in Maxwell's equations is that the choice of the formulation affects the numerical behavior. Okay? I should also add that that statement is completely independent of the numerical method. Right? We've also talked about numerical methods. And some methods are stable, others are not. That's a completely separate issue. Okay? But what I'm saying, even if you have a perfectly stable numerical method, you also need to have a well-posed problem. Okay? And it turns out that some formulations are well-posed, whereas other ones are not. Okay? This whole example with Maxwell's equation just is a motivation that I'm hoping makes you appreciate why it is that different formulations have a different numerical behavior, because they deal with numerical error differently. Okay? Okay, let's talk about GR now. Basically, if we stare at these equations, we see that the most important term is really the Ricci tensor. Okay? That is true in this 3+1 decomposition, but there are some approaches that actually don't use the 3+1 decomposition. They use Einstein's equations directly. They would have to deal with the four-dimensional cousin of this. There would be the four-dimensional Ricci operator. So either way, okay, it's always the Ricci tensor that has those second derivatives, and that's the term that we need to worry about, just like these mixed second derivatives in Maxwell's equations. Okay? So at the core in GR, okay, is the Ricci tensor, and I'll write it in this way where I'm not even committing to whether this is three-dimensional or four-dimensional. It takes the same form. Actually, it's on your formula sheet, right? I handed that out on Monday. So I can write this as the following. In terms of second derivatives of the metric, remember I told you 3 different forms for the Ricci tensor. This is one that is most common, perhaps in, well, I shouldn't even say that. Okay, here's partial C, partial B, GAB, minus partial A, partial B, GCD, and then we have a plus partial C, partial A, GBD, and a plus partial B, partial D, GAC, and then of course the nonlinear terms in the Christoffel symbols that I'm too lazy to write out. Okay? Now let's compare this with what we've seen for Maxwell's equations and for the wave equation. We see we have one term that has second derivatives, okay, that are arranged in such a way that this exactly gives us a Laplace operator. If we're thinking about a spatial Ricci tensor. If this is actually the four-dimensional Ricci tensor, then this operator gives us a wave operator. Okay? So either case, this one is fine. Okay? That gives us the term that we're looking for. Okay? For a wave equation. Okay? So in 3D, this is proportional to GAB, the Laplace operator, acting on the components of the metric. Okay? These 3 terms have the second derivative in different positions, all the different permutations of the second derivatives, just like the second term in Maxwell's equations, where we had the gradient of the divergence of A. Okay? So it is exactly these terms that again spoil the wave behavior. Okay? And here's the key observation. Just like in Maxwell's equations, where I was able to write these second derivatives as the first derivative of a new variable, gamma, I'm also able to write these three terms. This is a miracle, okay? These three terms I can write as a first derivative of a new variable, gamma, which is just a contraction of the Christoffel symbols. By the way, that explains why I chose the letter gamma for the divergence of A a minute ago, okay? So these terms can be absorbed, but can be absorbed in a term G, C, A, partial B, gamma C, okay? Where gamma C I define as G, dE, gamma C, dE. And again, I'm not really committing to whether this is 3-dimensional or 4-dimensional because it works in exactly the same way, okay? See, people knew that already in the 20s. De Donda and Lanchas, they worked with this in the 20s and worked it out, okay? Now, you can look up an identity. There's a neat way of writing this contraction of the Christoffel symbols. And I, yet again, refer you to problem 7.7 in the problem book. And, okay, and you'll find that this is the same as -1 over the square root of the determinant of the metric times partial A times square root of the magnitude of metric times GAB, okay? All right? Now you should be, you should find this remarkable because this looks like just like a divergence, right? Okay? And now how do we define, remember how do we define this new gamma variable in EM and M? We define it as the divergence of A. Now we could say, well, what should we do in GR? Well, here's our identification list. So we should replace A with the metric gamma ij. So we should now consider a new variable that is the divergence of gamma ij. And that's exactly what this is. Okay, so this is exactly the generalization of the quantity that we had in Maxwell's equation. By the same token, we were able to absorb these ugly derivatives in a derivative of this term. That's exactly the same thing. This gives us what I call form 3 of the Ricci tensor. Look at the important result sheet that I gave you, right? It's on there, okay? And so basically, this is at the core of reformulations of general relativity. Various different formulations do that differently. At the core of this is always something like this, where you write these ugly second derivative in terms of something else, okay? And that's basically the recipe, okay? Now the details are messy, okay? You have to do some math, but basically the big picture is exactly this, okay? So now how do different people do this? Well, there are different formulations, different people use different things. One formulation that I would like to mention is the generalized harmonic formulation, which does not use a 3+1 decomposition. It uses Einstein's equation in 4 dimensions immediately. You still introduce a slicing that makes things actually a little bit more complicated, but anyway, so that's called generalized harmonic formulation. Okay? And in this formulation that was developed by different people, including Helmut Friedrich, oh goodness, now I'm blanking on the name, but this is what Franz Pretorius used in his first successful simulations of binary black holes. In this case, actually, you solve the 4D equations, okay, and you impose the gauge by choosing gamma A, exactly those gamma A's, as some given function HA. Okay, you choose some functions as a function of the coordinates HA, okay? And these are then called the gauge source functions. Okay, so you use up your fourfold coordinate freedom to impose conditions on the four components of these gammas. Okay, that is at the core of this generalized harmonic coordinates. There's a special case where you choose h equals 0. Okay, that means that the gammas are 0. These gammas equal 0. That is referred to as harmonic coordinates. Okay. Somebody asked me earlier about where does this name harmonic slicing come from that I talked about earlier today. Harmonic slicing is just a version of harmonic coordinates where you only set the t component of this to 0, and in addition you set the shift to 0. One more comment here. One thing that is not as nice, I find, as in the 3+1 decomposition here is that in the 3+1 decomposition we impose the gauge with the lapse and the shift, and we have a very clear geometrical interpretation what the lapse and shift do. The interpretation of geometrically what these gauge source functions do, that is a lot less clear. Okay, but it's just a comment. Yes? Is this one choice of choosing gamma and this is another one? No, this is always true. Okay? This is always how you define the gammas. Okay? But now what happens is that the point is this. In the Ricci tensor, you now write the Ricci tensor in terms of derivative of these, right? And so you can do that in different ways. But one way would be to say I'll impose my gauge by setting these gammas to some given functions of the coordinates. And then when you evaluate your Ricci tensor, you just take derivatives of these given functions. Okay? But you have used up your gauge freedom. Okay? All right? Yes?
So how is there comparing trying to find an analogy between Maxwell's equation and the 3+1 decomposition ADM equation?
Right.
Now you're back to 4D.
As a little interlude. As just a little interlude, because I don't want to leave this out. This was a very successful formulation, okay? And that's why I wanted you to have heard about that formulation. But immediately right now, okay, I'm going to go back to a reformulation of the ADM equations, okay? So this was just a little interlude, okay? So you have not wasted days on developing the 3+1 formulation, if that's your concern, yes. Okay? All right? So another way of reformulating these equations that actually is used in many codes is what many people refer to as the BSSN equations, okay? And that stands for, well, the B is, I guess, my 15 minutes of fame, okay? And then, and it's Stu Shapiro, Shibata, and Nakamura, okay? And really this goes back even further to O'Hara and goodness, now I'm blanking on the name again. I'm not having a particularly good day today. I'm sorry about that, okay? But anyway, it goes back to other people, but many people refer to this. Can somebody help me out? Do you know what I'm talking about? O'Hara, it was Nakamura, O'Hara, and the K. You're not being helpful. Okay, fine. All right, so, sorry? Yes, who first worked out this form of the equations in 87. There's an 87. Oh, I think that's right, yes. Okay, so the point is this. We start with the ADM equations. Okay? So now you will be relieved to hear we are back at the 3+1. These equations, okay? We haven't thrown them out of the window, okay? And what we'll do is actually we take one more step, and that makes, I'll explain in a second why. We introduce a conformal transformation. This is our new friend from yesterday, right? That means we write the spatial metric gamma ij as psi to the 4 gamma bar ij. Okay? Except in this context, for whatever reason, it's more convenient to use e to the phi instead of psi. Okay, so we write psi equals e to the phi. Okay, that just makes the equations a little bit nicer, but it's exactly the same thing. Phi is now the log of the conformal factor and vice versa. All right. Now, also what this means is, in Cartesian coordinates, for example, basically, we discussed this at length yesterday, right? Basically, how many degrees of freedom are in here? Well, we can choose the overall scale. So in other words, we can freely choose the determinant of this conformally related metric. Cartesian coordinates, for example, we could make this determinant 1, all right? Why is that nice? Because then if I compute the equivalent of these guys, the three-dimensional guys, so everything is now in 3 dimensions, then you notice that, oh, this determinant will be 1. It's gone, and really it's literally just a partial divergence of the metric from partial derivatives, okay? So that's what makes this nice. Okay. Then what do? Well, we again split the Ricci tensor in exactly the same way as we did it yesterday when we walked through conformal transformations. So we've seen that, oh, no, actually, never mind. Yes, sorry, we write, goodness, so we write the Riemann tensor as one contribution that comes from the conformally related metric, plus other terms that come from our conformal factor, right? Which I now call phi. Remember we did this exactly yesterday, right? We said basically when we do this confirmation, these are the type of terms that we get. That's what we do again here. Basically we have, so when we go into these equations, when we see this Rij, we now say, okay, because we use this conformal decomposition, we split this term into these two guys. This one we compute from our gamma ij bars as, you know, in exactly the same fashion. And this one we compute from phi. Okay? Now the question is, in exactly the same fashion, which one? Because I gave you 3 forms of this Ricci tensor, and we used a form that again uses this gamma, the form 3. Okay? So in other words, we write R bar ij in terms of gamma I bar equals gamma Lm times ILM, which is 1 over the square root of gamma bar partial j and partial gamma bar times gamma ij. And again, in Cartesian coordinates, we can set this to 1. Okay? Okay, which makes this particularly easy. Okay. These gamma bar i's we now raise to the status of a new independent variable, exactly as we did it in E&M. And remember, I mean, keep in mind what we did half an hour ago for E&M. We introduced new variables, which were the divergence of the variable that is the equivalent of gamma in exactly the same way. What did we do next? Well, we derived an evolution equation for these gammas. Now you do exactly the same thing, okay? And how do you do that? Well, the partial t of this is basically, let's set this to 1, then we have divergence of this. So basically now we need to figure out, well, that's the evolution equation for gamma. We use this gamma, okay, up to the conformal transformation, but fine, okay? And then we used a second step for E&M. What was the second step? What did we add to that evolution equation? The constraint, and here you do the same thing. You add the momentum constraint, and then you get an evolution equation which gives you very stable, very well a formulation that is very well suited for numerical evolution. Okay, so we treat the gamma I bars as independent variables. That means that we need to derive an evolution equation for gamma for these variables, right? But we can do that in exactly the same fashion as Maxwell's equation. Actually, if you do that, if you find yourself doing that, you can actually take 2 sheets of paper. One has Maxwell's equations, which is very quick. We did it in the blackboard. And you just follow exactly the same steps. Okay? It works in exactly the same way. Right? And okay, as in E&M. Okay? And what you notice is, by going through this exercise, I have not made any assumptions for what these gamma bar i's are. In fact, I've completely maintained my gauge freedom. So I can still impose the gauge, choosing the lapse and the shift. So I have complete gauge freedom and can choose that however I think is well suited for evolutions of black holes or neutron stars or waves or whatever you may be evolving. Okay? So can still impose the gauge and slicing using beta I and the lapse alpha. All right? What can we do with this? Well, we've spent a whole week deriving all of these equations, going through a lot of formalism. Now we have about 10 minutes left to talk about black hole simulations. Okay? Let's talk about black hole simulations. These are not the only two reformulations that have been successful in GR. There are other ways of doing that. For example, a group from Meudon in France, they've developed a formalism that they call the Dirac formalism, that she uses certain more decompositions, and then evolves dynamically only the dynamic degrees of freedom GR. Okay, that's a nice way of doing it. There's also a formalism that's called the Z4 formalism that was suggested by Carlos Bona, which is also a nice formalism. It actually has similar ideas. Okay, they all boil down to basically dealing with those second derivatives. Okay, this Z4 formalism was actually brought into the same framework as this BSSN formalism. So there's a conformal version of that was developed by the group in Jena, and they actually have demonstrated that formalism, what they call this, the Z4C formalism, C for conformal. Okay, has some nice properties in keeping the constraints smaller than the BSSN formula. So there are developments, people experiment with different formulations. Clearly, I cannot cover all of them here, but this gives you an idea of what it is like. And really, my point was today to demonstrate to you why it makes a difference at all. Okay? I mean, why would you expect at all that a different formulation gives you a different numerical behavior? Okay? But let's actually talk briefly about black hole simulations. Okay, so we can, now let's imagine we have derived one of these formulations, or we've looked it up in the literature. Now we have written the code. We can now evolve these equations. So we can start, for example, let's say with two black holes. Yesterday we talked about how we set that up, right? We can use two black holes, maybe boosted in this direction, one boosted in this direction. So we have now a black hole in the binary orbit. Now let's say we have a code that can evolve these equations. Now we can follow these black holes in this binary orbit. The first question that we still have is, well, how do we choose the lapse and the shift? And whether this simulation is successful depends crucially on how we choose this lapse and shift. By experimentation, okay, it turns out there's a particularly nice set of coordinate conditions that guarantees or gives us stable evolutions. Is the following. Okay, so people had great success with a set of equations, the 1 plus log slicing, okay, which is a generalization of the slicing that I told you about earlier today, namely the harmonic slicing. Okay, so this is a generalization of harmonic slicing okay, and basically what you say is, well, this morning I told you this is minus alpha squared k, where k is the trace of the extended curvature, the mean curvature. But now I allow for an extra function that depends on alpha, and here's your k. Okay? And it turns out if we choose this function f of alpha as 2 divided by alpha, okay, then we can integrate this equation, okay, analytically, and we find that alpha will be, then alpha equals 1 plus log of the determinant of the gamma. Okay? I have a typo in my notes. There's a mistake. I believe that is right. Okay? I'll ask you to prove that today in the tutorial. All right? There's also another generalization of this, and that is to say, well, this is just a partial t. When we have a shift, it's more natural actually to introduce an advective term that tells us how this lapse evolves, and that we want to add a shift term, so that gives us an advective version. And then we have this equation, partial t minus beta I partial I alpha equals minus 2 alpha k. Okay? And that is a very successful gauge condition that people have used in binary black hole evolutions. Okay? Now, often this is combined with the following condition for a shift. Okay? We can impose this in different ways. I'm not actually going to write all the details, but there's a certain shift condition which is called the gamma driver. Okay? Because it drives the gammas, these gamma i's that are just introduced, to a certain simple solution, namely gamma bar i's is approximately 0. Okay? So this is how that's implemented. We don't have time to talk about right now, and it's not all that important. It's just basically these have been very successful. Combined, these are now sometimes called the standard gauge in numerical relativity, because many black hole simulations are done with this choice of the coordinates. Okay? What actually Sasha Husa and Mark Hanam and collaborators, what they've shown after these were found to be so successful, they analyzed what actually happens when you do this. So they then said, well, let's look at Schwarzschild. Okay? Let's see what kind of a geometry does Schwarzschild develop if we evolve Schwarzschild with these gauge, and they found the following. Okay? So for Schwarzschild, okay, basically for Schwarzschild, if you start with Schwarzschild data, for example, the form that I've given you in isotropic coordinates, you impose this gauge, okay, the standard gauge, then you'll find that the metric functions will not be time independent. In fact, they will evolve in some way. But the remarkable thing is they very quickly settle down to a new equilibrium. Okay, so now, of course, this is Schwarzschild. The geometry of Schwarzschild is what it is. There's no physics going on. We're only talking about a coordinate effect, right? But what happens with these spatial slices of Schwarzschild, when we evolve them with these coordinates, is that they settle down into a different shape. Okay? I gave you this picture of Schwarzschild in isotropic coordinates that goes from spatial infinity, go through an Einstein-Rosen bridge to another universe. What basically happens is they disconnect from the spatial infinity of the other slice. Instead, they settle down into a shape that looks like it approaches a long cylinder. Okay? And if you draw that shape, it looks like a trumpet. Okay? So the embedding diagram is now something like this. Okay? Now, if you stare at that long enough, it looks to you like a trumpet. Okay? And therefore, this is called the trumpet geometry of Schwarzschild. Okay? So these slices settle down to a trumpet geometry. Okay? What's nice about that is that, see, they never go to, they have a limiting value of the areal radius. That means is they never hit the space-time singularity. They never reach the space-time singularity. So this is one way of imposing or making sure that you avoid the space-time singularities in your numerical code, so your code never sees those singularities. That's why hand-wavingly these coordinates are successful. Okay? So they avoid the space-time singularity. Okay? And that warrants stable evolution. All right? Sorry? For this gauge choice, for 1 plus log slicing and the gamma driver. Okay? All right? Look, I'm so impressed with myself. I just wrote down the last word in my notes, and it is 1 o'clock sharp. We are done. Okay. Today, this afternoon, we still have a tutorial, but actually I covered all the material that I meant to cover this morning. So I hope this gave you an impression of how the evolution equations work, how you can use them, why different formulations work differently numerically. Should give you an overview at least, okay? So I'll see you this afternoon. Okay, so I would not have run out of this room without saying something either, but I thought I would say that this afternoon, okay? But basically, since we are already doing this, I should tell you that this has been really great fun. Okay, so I've really enjoyed talking to you. I've really enjoyed interacting with you. You've been super inquisitive, engaging. You've asked great questions. So I've really enjoyed this. So it's really been a pleasure to be here and talk to you about all of this stuff. Okay, so thank you very much for making it so much fun.